1 minus TD, which from here is, let's make sure I'm not messing up with something somewhere. Nope. TC times VD over VC. VD is just, this is, the volume here and the volume here is the same as we said before. This is just Vmax. Put down Vmax. And I'll just abbreviate it shorter to Vx. This right here is the minimum volume, which I will just abbreviate to Vn. So this becomes Vx over Vn to the 1 minus gamma minus Ta, which is just from that other relationship there, is Td times oh, that's right, because it's the reciprocal over there. Times Vx over Vn, 1 minus gamma, divided by Tc minus Tv. We can factor out the common factor. So that got 1 minus Vx over Vn to the 1 minus gamma over Tc minus Tv, or times Tc minus Tv over Tc minus Tv. And that reduces down to the efficiency of the Otto cycle, 1 minus Vx over Vn to the 1 minus gamma. All right, so all of that to come up with a new efficiency. Let's actually do some numbers here. So the maximum volume versus the smallest volume, because we have the piston that, I mean, I'm not drawing it to scale there, but it goes up pretty far and then it compresses pretty far. And if you're dealing with diesel engines, it compresses even farther. Because I guess that's diesel ignites from high pressure. So Vx over Vn is somewhere around 8. If we're dealing with air, and we went through some of this, and there's the table in the book, for air, gamma is about 1.4. So therefore, the efficiency of this particular engine would be 1 minus 8 to the 1 minus 1.4, which is 1 minus 8 to the 0.4, negative 0.4, which is 50-something%. %. All right. So potentially you can get greater efficiency if you can increase the ratio of maximum volume to lower volume, but by doing that, you're going to probably be involving larger cogs in order to pull it up that far, which will expend some of its own energy right there. Presumably, the ratio that it is now is, they've tried all sorts of stuff over the past 100 and some years. They've come up with presumably the most efficient, I would like to think. Questions? Then let's do the challenge problem. In the challenge problem, I have a tent sitting out in cold air. Overhead view, I have a tent. I've got a freezer compartment inside there. So this is the freezer compartment here. And this right here is the engine, or motor probably, better wording. And then I've got air out here. The temperature inside the freezer, negative 13 degrees Celsius. The temperature in the tent, 1 degree Celsius, and the temperature outside, 0 degrees Celsius. This is the starting point. The question is if we stick another freezer inside the tent that works just as well, what will be the temperature inside the tent? And that's what we're going to do. Engines, or the motors, use the Carnot cycle. And as we went through for the Carnot cycle, QC over QH is equal to TC over TH. So that's what the Carnot cycle gives us. If we expand that just a little bit further, I'm going to subtract 1 from each side. There are other ways of getting it if you were trying to figure this out for the first time. But so QC minus over QH minus 1 would therefore be TC over TH minus 1. Shocking, I know. Get a common denominator, so I have QC minus QH over QH equals TC minus TH over TH. So that's going to be QH. Should not stick an equal sign there. So QC done the other way. Now, QC minus QH is equal to QH over TH times TC minus TH. Putting it in the more traditional order, QH minus QC is equal to this times TH minus TC. And that right there is just about QH is the amount of energy coming in, QC is the amount going out of the engine there. Let's actually go for the other view of it. I have QC coming in. QC, because this is the colder temperature, the temperature in here is TC. I have QC going out. Energy coming in is minus the energy going out. Should stay the same. If I have a constant temperature here, there'll be QC coming out. And then I've got the hotter temperature out here. So I've got T hot right there. This is QH. And then in the tent, and then outside, I've got, I'll just call it T0. The temperature of the air. It's not the hottest or the coolest. Now, if I reach some sort of thermal equilibrium here, then these temperatures are going to stay as is. It's not getting any hotter or colder when I have just the one freezer in there. In order for that to happen, I have to have flowing out QH and then flowing in QC. So the temperature exchange through the tent here would be QH minus QC. So that just sums up into, I have QH minus QC going out. Because we've reached the steady state, QH is relatively constant. In order to keep this the same temperature, there's no reason for, we're assuming that the engine's not, as it warms up, is not changing the efficiency of it. We've reached some sort of steady state so that QH is a constant, TH is a constant, because again, steady state, these are the temperatures where they're staying. So this is just a constant, which I will label as A. Now, if you get further into it, you can figure out A actually, you can solve for A given enough information. This is sort of a side note. A is going to be the thermal conductivity times the area divided by the thickness of whatever the material you're trying to get through. When you're talking about at the tent, then it'd be the thickness of the material. Thermal conductivity depends upon what the material is, and then area. Well, if it's a big tent, then you've got a huge amount of surface area there. All right. One other piece of information. I have energy flowing into this section right here, and the rate at which that flows in depends upon the difference in temperature there. The whole QC equals some constants, which I'll label as B, times the difference in the temperature. Misprint right here. So employing that for the situation at the tent surface, I have QH minus QC is equal to A TH minus T0. So basically using this equation, just applying it at that interface. All right, we're time for I'm going to pause this for a moment. You probably should tell me I shouldn't say this next thing, but I'm going to anyway. All right. Do you know who Les Paul was? Inventor of the electric guitar. He and this person named Mary Ford were partners. And then, now that they died long ago, when I was working at DuPont, there was a woman there whose name was also happened to be Mary Ford. And I said, I want to apologize for what I'm about to say next, but I need to say it just to get it out of my system. So I said, how's Les Paul? And that was it. Never had the desire to say it, to connect her name with Les Paul again. So that was part of the reason for that. All right. I know that QC over QH is TC over TH, or we can just change that around a little bit. I know that QC over TC is equal to QH over TH. Well, I have a formula for QC right there. So I have B times TH minus TC over TC is equal to, well, QH is just QC plus that, so that's BTH minus TC plus ATH minus TO over TH. Now it's all becoming clear, I'm sure. There's a whole lot of subscripts here. I'm going to try to simplify this. So I'm going to let H be TH over TO, C equal TC over TO, and M to be A divided by B. A and B are just these constants related to the rate and how much energy is going to be flowing through. All right. To get into that state, I'm going to multiply both sides by 1 over B, and then multiply top by 1 over T sub naught and the bottom by 1 over T sub naught. So over here, the B's are going to cancel out. I'm left with TH over T sub naught, which is H, minus TC over C, or minus C over C. Over here, I get B canceling out, and I'm left with H minus C, plus A over B, which is M, H minus 1, divided by H. Hopefully that seems cleaner than what I had. I want to solve for M. I need to figure out that ratio in order to know what happens when I stick the other freezer in there. So in this first situation, solving for M, and so first thing is I'll multiply both sides by H. So I get H squared minus CH over, actually I'm going to multiply both sides by C also. It's equal to CH minus C squared plus MC H minus 1. I'll do a quick check, make sure it didn't mess up somewhere. Multiply the left side by H, I get this. Multiply the right side by H, I got that. Plus MC H minus 1. Okay, it's looking reasonable. I'm going to get this over to the other side. So I end up on the left-hand side with H squared minus 2CH plus C squared is equal to M H minus 1. And what is that?
Difference of square roots?
Square of differences. So it might be, this might be what you were thinking, H minus C squared.
Yeah.
Difference of squares. Yeah, I don't think difference of squares works in this case.
Okay.
Is equal to M, I've lost my C there, MC H minus 1. And so H minus C squared divided by C, H minus 1 is equal to M. At this point, we can actually come up with a value for M, this ratio of, I guess, the rate at which heat is leaving and heat is coming in. So I know that H is the hot temperature over the outside temperature, which is, fortunately, we're not doing degrees Celsius because it's divided by 0. Math people still have yet to figure that one out. So this is 274.15 over 273.15. C, it's going to be TC over T sub 0, which is 260.15 divided by 273.15. And plug and jump.
trouble finding it.
Seven, five, three.
1753.
Yeah.
Okay. All right. All of that to get to there, we'll take it to the next level. In our tent, we will now stick 2 of those freezers. The temperature of the freezers are still gonna be the same, it's still gonna be negative 13 degrees Celsius. The difference is it's gonna be dumping twice as much heat into the tent. This is still 0 degrees Celsius out here. This is inside here, negative 13 degrees Celsius. We assume the environment is big enough that it's not going to change its temperature. And what we're trying to figure out is the temperature, new temperature here, which I'll label as TH prime. Now, we've done a lot of the work already. We do have, since we have QC coming in here and QC coming in here, and actually coming out of the engine here, QH prime, QH prime. I guess it's H prime, not Q prime. So in essence, we have this, basically we double the heat exchange that's going through the surface of the tent. Now the tent hasn't changed, A is still the same. This has changed, that's still the same. This has changed because I've now got twice as much. So I have, for the second situation, I have 2 times QH minus 2 times QC is equal to A